Recording's rolling. It is Monday, May 12th. Gonna pick up in the Quantum Journal about where we picked up, about where we left off last week. Right, so, right before we get to that though, this is senior exams week. So, show you guys there are a couple of exam schedules. Right, so this week is senior exam week. So, any seniors I have, I will give you guys your final exam tomorrow because tomorrow is for social studies and science, it's a science class. Okay. Monday is ELA and math. Right? Tomorrow is social studies and science. Right? Wednesday is electives, makeup, and then makeup and makeup. Right? So that's for seniors. Now for everybody else, your final exams are for a couple of weeks. Well, all right, we got they start on Thursday the 22nd through Wednesday the 28th is for everybody else. Right. So that's exams. Right. So everybody all right so far? I know over the weekend, I was thinking back to about where we left off. We were at core fundamental forces, which is about to lead to the standard model, which we're about to look at. And right before that, we're looking at this question of how much free will do you have? Now, there are different perspectives on that. What is the sort of quantum mechanics perspective on that, which is just one perspective. And it did remind me of a couple other sources I saw. So here, I got a little bonus video for you guys from CGP Grey.
Your brain is two brains, two hemispheres, each doing half the work of being you. Half your vision goes to each and half your movement directed by each. Right controls left and left controls right. Your two brains coordinate through a wire of nerves, but this wire can be cut and was, for a time, used as an epilepsy treatment. After the cut, people seemed the same, though their brain was split in twain. Except some post-split patients described that while selecting their morning outfit with right hand, left might come along to disagree. Actually, left hand might quite often disagree, which these split brain patients found frustrating. What's happening? To investigate, remember, right brain sees and controls one half, while left brain controls and sees the other. But only left brain can speak. Hello. Because that's where the speech center is located. Right brain without this is mute. In normal brains, this doesn't matter because each half communicates across the wire with the other. But split brains can't, and thus you can show just the right brain a word, ask the person, what did you see, and you'll hear nothing. Because left speaking brain saw nothing. Meanwhile, right brain will use its hand to pick the object out of a pile hidden from left brain. This is deeply creepy. Ask why are you holding the object, and speaking left brain will make up a plausible sounding but totally wrong reason. I always wanted to learn how to solve one of these. Left brain isn't lying, it's just doing what brains do, creating a story that explains its past actions to its current self. A behavior which does rather cast doubt onto the notion of free will, but that's a story for another time. Creating reasons for why it does things is just something left brains do. It happens in normal, healthy humans all the time, and if you think about it closely, you know you've done this. Back to experiments. Give right brain an object, ask the person what's in your hand, and they won't be able to say. I'm not holding anything. And when asked to draw, a split brain can draw two separate objects simultaneously with each hand in a way unsplit brains find challenging. These experiments on split brain patients are deeply unsettling because they really point in the direction of a mute, separate intelligence, something living in the skull. You can even ask questions of a split brain and get disagreement on the answer. So if your brain is split, who is the you in this situation? From the outside, it's tempting to think of the part of the brain that's speaking as the person, but something is hearing and answering questions. And though right brain can't speak, it does understand faces, which left brain can't. If this is you, you don't know who your friends and family are in a crowd. This act of cutting exposes two minds in one head, and the talking mind doesn't know there's someone else in the house. The left brain can describe the situation it's in, but nonetheless will constantly be surprised by right brain's actions and explain them away. There's a question to be asked here. Why, after separation, does right brain not totally freak out, but instead plays along helpfully, answering questions and listening to left brain's dumb stories about what's happening? It's the best pony? I don't know. Speculation time, but one answer is the cutting doesn't make right brain a separate intelligence, consciousness, person, but rather it has always been. In normal people, perhaps right brain grows up as a companion without a choice, feeling at first somewhat equal partners, but then as speech develops that it can't participate in, that increasingly becomes the central point of life, it resigns to mutely coordinate with left brain. At this moment in your normal head, there are two of you watching this video, one having a mind equals blown moment and the other mentally rolling its eye at the obviousness of it all. In split brains, right doesn't freak out because not a whole lot has really changed. You might not agree and may be arguing right now why it can't be possible, exactly as we would expect talking left brain to do. Speculation aside, split brain patients show at the very least that in the mind there is a separate something that can hear and understand and respond given the right circumstances. Your brain isn't entirely yours. Who is you? You is too.
The objective of particle physics is to understand the basic structure and laws in nature, all the way from the largest dimension in the universe, formation of galaxies and stars, all the way down to the smallest dimension in the microcosm. So historically, we knew about all of the different elements in nature. We knew about helium, hydrogen, oxygen, gold, lead, and so on, which are all made of different atoms. But a great simplification was made when we realized all the atoms are just made out of three particles, the protons, the neutrons, and the electrons. And just by adding more protons, more electrons, we get the different elements, different type of atoms. In principle, you can build a very simple universe with just protons, neutrons, and electrons. But it became much more complicated in the beginning of the 20th century when we found many, many new particles from cosmic rays. There wasn't really a system established to organize this zoo of particles. So we were calling these new particles things like pi, sigma, delta, and so on. And things got so bad, we were running out of symbols to name these particles. So we started organizing these particles according to the properties they had. And the properties are things like spin, electrical charge, so if they're positively charged, negatively charged, or neutral, mass of the particles, and the lifetime of the particles, which is how long it takes before they decay into lighter particles. To simplify the picture, new fundamental particles called quarks were predicted. And the whole zoo of particles could be described by combinations of these quarks. And this was the birth of the Standard Model. At the beginning, there were only three quarks. Then a fourth, fifth, and sixth quarks was predicted and then discovered, and this gave us great confidence in the model. In addition to these quarks, there's another set of fundamental building blocks of matter, the so-called leptons. They're composed of an electron, their heavier cousins, the muon and the tau, and their neutrino partners. In addition to the fundamental building blocks of matter, the Standard Model also incorporates the fundamental forces. The exchange particles of the weak force are the W and the Z boson. The weak force explains the energy production in the sun and is responsible for the radioactive beta decay. The electromagnetic force acts on charged particles. The corresponding force carrier is the photon. The electromagnetic force is responsible for propagation of light or for the fact that a magnet can pick up a paperclip. The strong interaction acts on the quarks. The corresponding force carrier is the gluon. The gluon literally glues together the quarks in the neutrons and the protons, and it holds the nucleus together. The Standard Model is extremely.
All right, and actually that one I have its own special quadrant for, so pause that right there. All right, so this is the standard model right here. The standard model is to particle physics what the periodic table would be to chemists. If you ask the chemist what makes everything in this room, they'll point to the periodic table and say, oh, some combination of those elements there. But you talk to a particle physicist, they'll say, well, actually, all those elements of the periodic table are just combinations of protons, neutrons, and electrons. And there's more particles than just those. Like where does photons fit in that model, right? For example, right? So they've come up with this right here. So we got here's your 6 quarks, here are 6 leptons, and these 5 bosons over here. Okay. Now, what I see is elementary. I see electrons, like electrons are elementary. I see photons right up here. So here's electrons, here's photons. I don't see anything about protons or neutrons though, because protons and neutrons turns out are actually composed of these two, like 2 ups and a down versus 1 up and 2 downs, right? For proton versus neutron. All right, so here you go. We've got these 17 elementary particles, which are divided into these categories, like this. It's got fermions and bosons. Okay. They're organized by mass, charge, and spin. And that was the numbers on here. Got a little key over here, mass, charge, and spin. Right, boom, boom. Right, got some numbers. Okay. Okay, and some other details. Right, here's a proton. Here's a neutron. It's made of 2 ups and a down, 1 up and 2 downs. Right. An electron actually is elementary. Photons are elementary. Right. I've got other kind of particles there. Okay. And so this model was worked out by theoretical physicists back in the 1970s. And these particles have been experimentally verified by particle collisions and aggregate statistics in the intervening decades. And the last one to be experimentally verified is, the next one I got queued up here, which is a Higgs boson, which is related to something called the Higgs field, and somehow gives particles mass, right, which we're about to be looking at pretty soon. Okay. Now, the standard model looks like it pretty thoroughly explains right, anything related to quantum mechanics or electromagnetism or the 2 nuclear forces. But what's the connection with gravity or general relativity? The standard model doesn't seem to have a clear connection to that. Okay. So is there some wider model that could encompass both the standard model and gravity, general relativity? Maybe that would be called unification or the theory of everything, which scientists are still on the hunt for something like that. But anything on the small level explained by that. There you go, standard model. Where? Which one? Quarks, leptons, or fermions, they call fermions.
Let's cut to the chase. As of July 4th, 2012, the Higgs boson is the last fundamental piece of the standard model of particle physics to be discovered experimentally. But you might ask, why was the Higgs boson included in the standard model alongside well-known particles like electrons and photons and quarks if it hadn't been discovered back then in the 1970s? Good question. There are 2 main reasons. First, just like the electron is an excitation in the electron field, the Higgs boson is simply a particle which is an excitation of the everywhere permeating Higgs field. The Higgs field, in turn, plays an integral role in our model for the weak nuclear force. In particular, the Higgs field helps explain why it's so weak. We'll talk more about this in a later video, but even though weak nuclear theory was confirmed in the 1980s, in the equations, the Higgs field is so inextricably jumbled with the weak force that until now we've been unable to confirm its actual and independent existence. The second reason to include the Higgs in the standard model is some jargony business about the Higgs field giving other particles mass. But why does stuff need to be given mass in the first place? Isn't mass just an intrinsic property of matter, like electric charge? Well, in particle physics, no. Remember that in the standard model, we first write down a mathematical ingredients list of all the particles that we think are in nature, and their properties. You can watch my Theory of Everything video for a quick refresher. We then run this list through a big fancy mathematical machine, which spits out equations that tell us how these particles behave. Except, if we try to include mass as a property for the particles on our ingredients list, the math machine breaks. Maybe mass was a poor choice, but most particles we observe in nature do have mass, so we have to figure out some clever way of using ingredients that will spit out mass in the final equations without it being an input. Kind of like how you can let yeast, sugar, and water ferment into alcohol that wasn't there to begin with. And as you may be thirstily anticipating, the solution is to toss a yeasty Higgs field in with the other ingredients of the standard model, so that when we let the math ferment, we get out particles that have mass. But this model also brews up something we didn't intend, a solitary Higgs particle, the infamous boson. And since the model works so well to explain everything else, we figured it was pretty likely that the lonely boson is right too. To summarize, the Higgs boson is a particle which is a leftover excitation of the Higgs field, which in turn was needed in the standard model to 1. Explain the weak nuclear force, and 2. Explain why any of the other particles have mass at all. However, the boson is the only bit of the Higgs field which is independently verifiable, precisely because the other bits are tangled up in the weak nuclear force and in giving particles mass. The fact that the Higgs boson is so independent from the rest of the standard model is why it's the last piece of the puzzle to be discovered. And if it turns out to be exactly what was predicted, the standard model will be complete. The only problem is that we know the standard model isn't a complete description of the universe. It entirely misses out on gravity, for example. So to physicists, it would be much more interesting and helpful if the Higgs boson turns out to be not quite what we expect. Then we might get a clue as to how to reach a deeper understanding of the universe. Let's cut to the chase. How does the Higgs field give particles mass? And to be clear, we're talking about the Higgs field and not the Higgs boson, which is merely an excitation left over after the process we're about to explain. But I digress. Back to mass. To begin, we need to know what we even mean by mass. So we'll head the other direction and talk about what it means to be massless. This may sound crazy, but the defining feature of any particle without mass is that it travels at the speed of light. In fact, if we're honest, it should really be called the speed of massless particles. But since the first massless particles we knew about were photons of light, the name has stuck. Anyway, the point is that all massless particles travel 300 million meters every second. The details of this are explained by special relativity, but simply put, it's physically impossible for a massless particle to not travel at 300 million meters per second. And so mass is just the property of not having to always travel at the speed of light. As a side effect, this also means not being able to travel at the speed of light, but the key is that particles with mass are lucky enough that they get to travel at any speed they want, as long as it's slower than light. The amount of mass something has just tells how hard it is for it to change from one of these speeds to another. Now, in part 1, we mentioned that if there were no Higgs field in the standard model, all particles should be massless and thus travel at the speed of light. But you and I and Swiss cheese clearly have mass, because we have the beautiful luxury of being able to sit still. So how does the Higgs field help us do that? Well, while massless particles can only travel at the speed of light, they are allowed to bounce off of things. Things like particles, which are really just excitations in a quantum field. For example, the electron field is more concentrated at certain places, called electrons, and everywhere else is empty space. But the Higgs field is unusual in that it has a high value everywhere. And to be clear, this high value is not the famous Higgs boson. That's an extra excitation in addition to this already elevated field. But because the Higgs field has this everywhere non-zero value, any particle that can interact with it is pretty much bouncing off of it all the time. And if a massless particle bounces back and forth, or since it's quantum mechanics, does both at the same time, then even though in between bounces it travels at the speed of light, when you add everything up, it looks like the particle is going slower than light, maybe even like it's not moving. And since only things with mass are allowed to not move, our massless particle now looks and acts like it has mass. Well done, Higgs. What's more, the Higgs field can even interact with its own excitations, which is to say, it can give mass to the Higgs boson too. Actually, the Higgs field likes to interact with itself so much more than with the lowly electrons and protons that make us up, that the Higgs boson has a great deal more mass. But we shouldn't complain, because even though the Higgs has given us a lot of trouble and only a little bit of mass, at least we have mass, which allows us the simple pleasure of not moving. Suppose you want to discover a particle. First, we need...
Wait a second, Henry. Did you just say that you're setting out in advance to discover a particle? How is that even discovering? Isn't that a little like Europeans discovering continents where millions of people already live? I mean, it's not really discovery, is it? It's more scientific fact-checking.
Exactly. Thanks for walking us through that point, John. If we're honest, we should say that the mathematical model for the Higgs was discovered in the 1960s, but the particle itself wasn't confirmed until 2012. In fact, the Higgs boson isn't even the first new particle to be uncovered at the Large Hadron Collider. The Xi-B particle, basically a heavy version of the neutron, was actually found several months earlier. You probably didn't hear much about it because the Xi-B is just a combination of quarks that we already know exist. So it's not really that exciting. I mean, if you know about cheese and you know about crackers, then the discovery of cheese and crackers, as delightful as it may be, isn't likely to upend your universe. But the standard model of particle physics also predicts something beyond cheese and crackers. That is, about 1 out of every bajillion collisions should produce a Higgs boson, which then decays into everyday stuff like electrons and photons, which are the same crumbs we catch in the detector all the time. This battle between the tiny chance for a collision to have produced a Higgs-like particle versus all the trizillion other collisions that produce similar crumbs is part of why we need a big machine like the Large Hadron Collider at all. There were earlier accelerators that had enough energy to create Higgs bosons in principle, but they couldn't actually do enough collisions to be confident they were actually seeing a Higgs boson and not just an assortment of crumbs that looks by chance like it's from a Higgs boson. It's kind of like trying to find out if a 20-sided die is rigged. Maybe you suspect it's twice as likely to land on a 3 than on any of the other numbers, but how can you check? Well, that sounds easy enough. Just roll the die a few times, and if you see extra 3s, it's rigged, right? Not so fast. For example, if you roll the die 10 times, there's a pretty good chance that you won't get any 3s at all. That's because even though rolling a 3 is twice as likely as each other number, there are still a lot of other numbers you could roll. So random chance and big numbers can be surprisingly deceptive. Even if you roll the die 100 times and do get an excess of 3s, this is still expected to happen with a fair die once every 50 times. How much are you willing to bet that you actually have evidence for a new particle if there's a 1 in 50 chance you get these results by random fluctuation, even if the particle doesn't exist? What if a Nobel Prize is on the line? How sure do you want to be? 1 in 1,000? 1 in 10,000? Actually, physicists are even more stringent. When we say we've discovered a particle, it's because if the particle didn't exist, there would be less than 1 in a million chance of us getting the results that we do. So if you want to convince a particle physicist that you've discovered an unfair die, you'll need to roll it over 550 times to satisfy them. And that's just to check if a 20-sided die is rigged. There are far more than 20 possible outcomes of a high-energy particle collision.
Ooh, yeah, you guys saw all those diagrams flash across the screen. That's actually where I'm gonna pause this right here. Right, so that right there is called a Feynman diagram. That can show many different types of collisions. Right, so how are we gonna make sense of that? And what is this Higgs field, Higgs boson and math? Here, right, so yeah, starting from the theoretical framework that was worked out in the 1970s, there should be this everywhere permeating Higgs field, and some particles interact with the field and some don't. Now, anything that does not interact with with this Higgs field would not have mass. Okay? And that's right here. I'm looking at photons and gluons specifically. Okay? And anything that doesn't have mass has to move at the speed of light. Okay? So why does anything have mass? Well, last semester, maybe that wasn't a huge question. Like, here, got this point mass here. Why does it have mass? Well, isn't mass just a property of matter? And give it a push, it has some inertia and pushing again. Well, if you get to particle physics, not so much, right? Even if you look within an atom, say what's the mass of a proton, the answer differs whether you're talking about a hydrogen atom or a helium atom or a uranium atom. Right? All those have different mass protons within them. Right? So what does give something mass? Well, it's if that particle interacts with the Higgs field, and some particles interact more with the Higgs field and they're given more mass. Okay? So what is this Higgs boson? This Higgs boson is just the field interacting with itself. Okay? So it's an excitation in the Higgs field. Now, this was the last part of the standard model to be experimentally verified. Right? So you guys remember these 17 elementary particles? Right? Here's your Higgs boson right here. Okay, it's the most massive of all these. We've got 125 giga electron volts per speed of light squared. There's one way to quantify how massive something is, right? Like energy per speed of light squared. Right. Now, of course, nobody has photographs of any of these particles, right? Because that would really be a thing. But you can determine their existence by, first of all, having a theoretical framework that says that, well, ideally, if this model exists, they should exist, right? So, model from the 1970s. Okay. But then looking at collision data, like how do you empirically gather evidence to support this model, right? So they run billions and billions of particle collisions, and based on the data that comes out of the particle collisions, they can say statistically whether or not these particles would exist. Right? So what is the standard in particle physics for making a discovery? Because different sciences, there are different levels of probabilities. Like for many experiments, if you get something that, well, if it's, let's say, like within 5%, like if it's out on the tail of a normal distribution curve, and it's like, okay, well, if this really were random, then there would only be a 5% chance that it would nullify the null hypothesis, right? Or falsify the null hypothesis. Then that becomes normally publishable. Right? And then if you get like within 1% or 0.1%, right, that's even stronger evidence that your theory is correct. And so what's the standard in particle physics? It's called a 5 sigma standard. So that's to say 5 standard deviations from the mean, right? or another way to say is that you're so far out on the tail that if the particle collision data that you're getting were truly random, and it just by a stroke of luck of the universe, like looked like it was representing a Higgs boson, the chance of that happening would be approximately 3 in 10 million. Right? So by 2012, they had enough data from over the years to verify that yes, this particle does exist, and the chance of it not existing would be on par with winning the lottery. Okay, so there you go. All right, Higgs boson. All right, you guys go with that one? All right, so right where I paused the video, they were flashing a bunch of Feynman diagrams. We're going to do a real simple Feynman diagram here. All right, so let's get a couple of axes. On the vertical axis, I'll put time, and the horizontal axis, put space. Okay, which you guys know is backwards from all the labs you guys did, especially last semester. But I don't know, for some reason, when you get to relativity and quantum mechanics, I'm sure there's some logic behind it that I don't know. It's conventional to actually switch it up and put time on the vertical axis for some reason. All right, so time is ticking forward, going up. Now space could be in 3 dimensions, but let's just narrow it down to 1 dimension. Get something going on here. Okay, and then what's an example of, again, just a real simple Feynman diagram. You might have a couple of interacting electrons is all I'm going to do here. Right, so I got an electron here, I got an electron here, and where they interact, right, maybe get a photon released, which what that wavy line is, and then comes from that. I have a positron and a positron. Okay. Now, do you guys see how these arrows look like they're going backwards, like against time? That's a convention for representing an antiparticle. Okay. So an antiparticle might look like a particle, except it has exact opposite properties of everything. So instead of a negatively charged electron, we have a positively charged positron. Right? So the charge is opposite. The spin would be up. The mass would be actually negative. Okay, so antiparticles have negative mass. Okay, so that's a few particles interacting. Now, what's all the categories of particles you tend to see on these Feynman diagrams? I'll give you guys a key. There are going to be 4 symbols here. So if you see a solid line like that, that'll be a fermion, which is, of course, most of the particles on the standard model. So any of these 12 right here, any of those 12 would be fermions represented by a solid line. Right? For example, these electrons right here. Okay? If you see this wavy looking line, that's reserved for a photon. They relate to electromagnetism. If you see this this curly looking symbol, that'd be a gluon. Okay? It's like a strong force, I'm thinking. And if you see that dashed line, that's any other type of boson. So there you go. So symbols on a Feynman diagram.
Classical computer performs operations using classical bits, which can be either 0 or 1. Now, in contrast, a quantum computer uses quantum bits, or qubits, and they can be both 0 and 1 at the same time. And it is this that gives a quantum computer its superior computing power. There are a number of physical objects that can be used as a qubit: a single photon, a nucleus, or an electron. I met up with researchers who are using the outermost electron in phosphorus as a qubit. But how does that work? Well, all electrons have magnetic fields, so they're basically like tiny bar magnets. And this property is called spin. If you place them in a magnetic field, they will align with that field, just like a compass needle lines up with the magnetic field of the Earth. Now, this is the lowest energy state, so you could call it the 0 state, or we call it, for the electron, spin down. Now, you can put it in a 1 state or spin up, but that takes some energy.
If you took out the glass from your compass, you could turn the needle the other way, but you would have to apply some force to it. You have to push it to flip to the other side. And that is the highest energy state. In principle, if you were so delicate to really put it exactly against the magnetic field, it would stay there.
Now, so far, this is basically just like a classical bit. It's got 2 states, spin up and spin down, which are like the classical 1 and 0. But the funny thing about quantum objects is that they can be in both states at once.
Now, when you measure the spin, it will be either up or down. But before you measure it, the electron can exist in what's called a quantum superposition, where these coefficients indicate the relative probability of finding the electron in one state or the other.
Now, it's hard to imagine how this enables the incredible computing power of quantum computers without considering two interacting quantum bits. Hello. Hi. Now there are four possible states of these two electrons.
You could think that, well, that's just like 2 bits of a classical computer, right? If you have 2 bits, you can write 0, 0, 0, 1, 1, 0, 1, 1. Right? There's 4 numbers. But these are still just 2 bits of information, right? All I need to say to determine which one of the 4 numbers you have in your computer code is the value of the first bit and the value of the second bit. Here instead, quantum mechanics allows me to make superposition of each one of these 4 states. So I can write a quantum mechanical state, which is perfectly legitimate, that is some coefficient times this, plus some coefficient times that, plus some coefficient times that, plus some coefficient. So to determine the state of this 2-spin system, I need to give you 4 numbers, 4 coefficients. Whereas in the classical example of the 2 bits, I only need to give you 2 bits. So this is how you understand why 2 qubits actually contain 4 bits of information. I need to give you 4 numbers to tell you the state of this system. Whereas here I only need 2. Now, if we make 3 spins, we would have 8 different states. I need to give you 8 different numbers to define the state of those 3 spins. Whereas classically, it's just 3 bits. If you keep going, what you'll find is that the amount of equivalent classical information contained by n qubits is 2 to the power n classical bits. And of course, the power of exponentials tells you that once you have, let's say, 300 of those qubits in what we call the fully entangled state, so you must be able to create these really crazy states where there is a superposition of all 300s being one way and another way and another way and so on, then you have like 2 to the 300 classical bits, which is as many particles as there are in the universe.
Ooh. Yeah. Crazy detail right there. Come on. All right, so that whole computer file I just played, that whole video, really is just a file sitting on a disk, and it's just a string of zeros and ones, right? Just a classical computer, zeros and ones. Okay? So that's called binary. Your DNA has A, T, C, and G, so that's like quaternary. That's another way to store information. Some scientists talk about actually using DNA to store computer files too, which might have a lot of advantages too. Right? But here's another way: is quantum computing. Is what if you don't have classical bits? What if you have these qubits? Now, you guys remember? Think back to Schrodinger's cat, for example, to use as a mental model. Remember that cat could be both dead and alive simultaneously. It was in this entangled superposition of states. Well, could you have bits that are in this entangled superposition states? Yeah, you could have 0 and 1 simultaneously. Right. Now, the catch is, of course, when you make a measurement, it has to fall back into one of those classical states, either a 0 or a 1. Right. But before you make the measurement, before you make the observation, it could be in that entangled state, both a 0 and a 1, which means that how much information you could potentially have in a string of qubits is 2 to the power n equivalent classical bits of information, because it multiplies by 2. It's exponential, right? 2, 4, 8, 16. So like 3 qubits. Well, by the time you get around to measuring it, the first qubit could end up reading as a 0 or a 1, right? And when it's entangled, it's both a 0 and a 1. So there's 2 options there. The next qubit is also 2. The next qubit's 2, right? So that'd be 2 times 2 times 2, or 2 to the power of 3. That'd be equivalent to 8 classical bits of information. It's like, okay, so right, 3 qubits equivalent to 8 classical bits. Right? Is that a big deal? Well, it ends up being a big deal because this is an exponential curve. So by the time you get to 300 of these qubits, which again could be like smaller than your eyes could detect, right? If you're like storing these on atoms or something, right? But you do 2 to the power of 300, right? And that's equivalent to the number of particles in the observable universe, right? Which is mind-blowingly crazy. I mean, that's something bigger than our minds can even fathom. think about all the atoms that you are made out of. Now, already that's crazy, right? Like how many nitrogen and oxygen and carbon atoms are in each one of us, hydrogen atoms, right? Expand that to the entire planet Earth, extend that to our entire solar system, extend that to the entire galaxy. And then we're looking around the universe, we can see billions of galaxies. 2 to the power of 300 is pretty close to how many like atoms there are in the observable universe, right? Like how many hydrogen and carbon and everything crazy out there, right? Right. And yet all this information is able to be stored on like 300 qubits, right? So 300 qubits could store like a universe worth of information, which is great, right? And so now this is a developing technology, right? So quantum computers aren't fully fleshed out. They have some basic rudimentary quantum computers. So what's going to be the consequence of this? I mean, this might open up some good possibilities, and there might be some bad things too. Like one of the problems that comes with quantum computers is the question, like, how do you encrypt anything? How do you store passwords? Because if you have a 12-character password and somebody tries to crack your 12-character password classically, that might take years, right? Even if you have like big room full of computers, it might take years to crack your password, right? But a quantum computer might just put these bits in a superposition of states and crack your password in less than a minute. Okay, so could that cause problems in our lifetime? Maybe, or so. Just think about it. All right, we're gonna do one more today. Maxwell's demon.
The true nature of information would first be hinted at, thanks to a strange problem, one dreamed up by a brilliant Scottish physicist who appeared to be thinking about something else entirely. James Clerk Maxwell was one of the great minds of the 19th century. Among his many interests, Maxwell became fascinated by the science of thermodynamics, the study of heat and motion that had sprung up with the birth of the steam engine. Maxwell was one of the first to understand that heat is really just the motion of molecules. The hotter something is, the faster its molecules are moving. This idea would lead Maxwell to dream up a very bizarre thought experiment in which information played a crucial role. Maxwell theorized that simply by knowing what's going on inside a box full of air, it would be possible to make one half hotter and the other half colder. Think of it like building an oven next to a fridge without using any energy. It sounds crazy, but Maxwell's argument was extremely persuasive. It goes like this. Imagine a small demon perched on top of the box, who has such excellent eyesight that he can observe accurately the motion of all the molecules of air inside the box. Crucially, is in control of a partition that divides the box into two halves. Every time he sees a fast-moving molecule approaching the partition from the right-hand side, he opens it up, allowing it through to the left. And every time he sees a slow-moving molecule approaching the partition from the left, he opens it up, allowing the molecule through to the right. You can see what's going to happen. Over time, all the fast-moving hot molecules will accumulate on the left-hand side of the box. and all the slow-moving cold molecules on the right. Crucially, the demon has done this sorting with nothing more than information about the motion of the molecules. Maxwell's demon seemed to say that just by having information about the molecules, you could create order from disorder. This idea flew in the face of 19th century thinking. The science of thermodynamics had shown very clearly that over time, the entropy of the universe, its disorder, would always increase. Things were destined to fall apart. But the demon seemed to suggest that you could put things back together without using any energy at all. Just by using information, you could create order. It would prove to be a fiendishly difficult problem to solve, not least because the brilliant Maxwell had come up with an idea far, far ahead of its time.
It's amazing the impact he had on physics, and that he came up with this very intricate concept, and that he already, in some sense, anticipated the notion of information that wasn't actually there at that time. There was no such thing.
I think this idea was astonishing. He didn't really have a resolution. He raised it as a concern, and he left it open. And I think what followed is more or less 120 years of extremely exciting debates and developments to try to resolve and address this concern.
So what was going on with Maxwell's demon? It may sound far-fetched and fanciful, but imagine the possibilities if we could build a machine in the real world that could mimic the actions of the demon. I could use it to heat a cup of coffee, or to run an engine, or to power a city, all using nothing more than pure information. It's as though we could create order in the universe without expending any energy. Scientists felt intuitively that it had to be wrong. The problem was it would take over 100 years to solve the problem. It's a really difficult idea to get to grips with, but information, everything from a Beethoven symphony to the contents of a dictionary, even a fleeting thought, all information needs to be embodied in some form of physical system. Amazingly, the reason we understand the true connection between information and reality is because of Maxwell's demon. Remember, it seemed like the demon could use information to create order in a box of air that started out completely disordered. Moreover, it could do this without expending any effort. Information seemed to be able to break the laws of physics. Well, that's not true. It can't. The reason why Maxwell's demon can't get energy for free lies here, in his head. What was discovered was this. The demon really is using nothing more than information to create useful energy. But this doesn't mean that he's getting something for nothing. Remember how the demon works. He spots a fast-moving molecule on one side of the box, opens a partition, and lets it through to the other side. But each time he does that, he has to store information about that molecule's speed in his memory. Soon, his memory will fill up, and then he can only continue if he starts deleting information. Crucially, this deletion would require him to expend energy.
The demon needs to keep a record
of which molecules are moving where. And if the record-keeping device is only finite size, at some point the demon's going to have to erase it. That's an irreversible process that increases the entropy of the universe. It's the erasure of information that increases entropy once and for all.
What was discovered is that there's a certain specific minimum amount of energy, known as the Landauer limit, that's required to delete one bit of information.
Ooh, all right, and that's the answer to the question there. It's called the Landauer limit. All right, so what we got from this? All right, so we're going back to about the 19th century. You guys remember with learning about the laws of thermodynamics a few weeks back? Okay, so there was the first law, it's basically conservation of energy. There's the second law, so a bit more abstract, has something to do with entropy and a time order of processes. Okay, so like if you have a hot tank next to a cold tank, they'll reach an equilibrium temperature. And if you run the calculations on entropy, like you guys did, you say, well, the hot tank cooling down loses entropy, the cold tank heating up, that gains entropy. But overall, there's always an increase in entropy for spontaneous processes at large, and increase in entropy for the entire system or for the entire universe. Okay. There is also that kinetic energy theory of temperature. So what if you had like some, now he's calling it a demon, but that was back in the 19th century. Nowadays, we might just call it a computer, right? There's some computer system that has some detector and maybe is able to allow fast particles to the left side and slow particles to the right side, effectively separating the hot from the cold. Ooh, right? Now, at a glance, you could say, well, if you had this running at near 100% efficiency, would this actually break the second law of thermodynamics, right? You could build a boiler next to a refrigerator with pretty much zero energy input. Right? I could run a power plant and the whole air conditioning system and not have to have any fuel source. Okay? Now, it took people a long time to come up with the solution to this. They figured finally the answer is still going to be no. And it has to do with this really weird aspect of the universe that information has to be embedded in physical systems. And to erase this information, came up with this number, requires 0.018 electron volts to erase one bit of information, and that's called the Landauer limit. And you can run the calculations that the increase in entropy by erasing information would outweigh the decrease in entropy by this process of separating hot from cold. So this wouldn't actually work. That is a wrap on the video today.